One of the first things we learn about shapes and geometry is the concept of parallel lines. Two lines that both travel in the same direction and their paths never cross. Well, let me tell you, reality is a lot more complex. All our lives we've been told we live in a three-dimensional space, or the third dimension, those dimensions being height, width, and depth. Now this is superficially correct, and thinking any different won't change your life, but the reality is we exist within a four-dimensional realm called space-time. We have freedom of movement within three of these dimensions, space, but the fourth, time, is restricted. This means I can move in any direction within space at any speed or any acceleration. My only constraint is the energy needed to change my momentum. But in the fourth dimension, time, I can only go one direction at one speed. For that reason, we are considered three-dimensional beings. We don't possess the ability to comprehend the fourth dimension. But that doesn't mean it doesn't exist, and believe it or not, it's why things are attracted to each other by what we call gravity. In order to comprehend space-time and how the fourth dimension creates gravity, we need to be able to comprehend how higher dimensions affect lower dimensions. So to begin, let's pretend we have a pair of one-dimensional friends, friend A and B. And these friends, they get in a fight and decide, I'm done with you, and they start walking away from one another in opposite directions. Then, after a while, all of a sudden, friend B pops up out of nowhere and both of them lose their minds. How is this possible? There's no conceivable notion, other than teleportation, of how these two friends could possibly meet up again. Their one-dimensional minds are just unable to comprehend what is happening, because their world is actually a circle within two dimensions. However, without information from the second dimension, it's impossible to know the true direction of their path, or any path for that matter. Therefore, the one-dimensional friends are bounded by the second dimension. The same thing happens for those living in two dimensions. These friends walk away from each other, turn 90 degrees to their north, keep walking in parallel lines, and yet somehow they run into each other. That is because they actually exist upon a sphere. Again, without information of the third dimension, it's impossible for them to conceive the true nature of the path they are taking. That brings us to our world, the third dimension. And yes, we too are bounded by a higher, the fourth dimension. Just like our friends in the previous two examples, there's no way for us to conceive exactly how we can travel in straight parallel lines and meet up again, but we can understand that our plane of existence is curved in the next higher dimension. What does that mean? We have no idea, just like our friends from before, but that doesn't mean we can't understand the consequences of it. This curvature in the fourth dimension is what we experience as gravity, and just like how everything in the lower dimensions that travel in straight parallel lines eventually meet up, the same thing happens here in the third dimension. However, here things differ a little from our friends before. Unlike our lower dimensional friends, we don't have the freedom to choose how fast to move through our four-dimensional space-time. Whether you are running, sitting, or falling, you are moving through space-time at the notorious speed c, roughly 300,000 kilometers a second. This is of course the same c from the famous E = mc squared postulated by Einstein, and it is equally distributed between space and time. So, if you decide to move faster through space, you must move slower through time. And if you were to somehow slow down in space, you'd move faster through time. Now you may be thinking, well, I'm just sitting here, why isn't time passing faster? But remember, the planet's surface is moving, the Earth is moving, the solar system is moving, and the galaxy is moving. It's impossible to stop moving through space. Plus, your changes in velocity are so small compared to c, the difference is imperceptible. Even rockets that travel at 8 kilometers a second are only moving 2/10,000% of the speed of light. So we are constantly moving through space-time at a constant speed, and since space-time is curved, just like the previous examples, our perceived straight paths appear to attract or converge with one another. If this still isn't making sense, don't get discouraged. We are talking about a very complex concept, normally outside our realm of comprehension. But bear with me, we're going to start visualizing this, and I think you'll have the same eureka moment I had. Okay, let's start visualizing this. To begin, we'll start with the most common visualization of gravity, but it's not my favorite. We'll visualize the fabric of space-time as a trampoline. Now normally, empty space-time just looks like a trampoline. But of course, space-time is not empty, it's filled with matter, normal and dark alike, and this matter has a very strange effect on space-time. Now, although they exist within space-time, the elementary particles that make up all matter are not made up of space-time themselves. They are, for lack of a better term, and as far as we know today, pure energy. And this pure energy occupies volume within space-time, or disturbs it. But this volume that should be space-time doesn't simply disappear because energy or matter is occupying it, it is displaced. So the more energy or mass that exists, the greater a disturbance and displacement it has on the surrounding spacetime. So planets and stars and all energy within them warp spacetime around them. That means spacetime is curved by matter, which is very important because straight lines on curves have unique behaviors. A straight line along a curve is called a geodesic, and an easy way to identify geodesics on spheres is that they always pass through the point on the exact opposite side of the sphere. The only reason it wouldn't is if some force was applied to it along its path, but then it would no longer be a straight line. Now, two geodesics, no matter where you put them on a sphere, will cross each other's paths. Now, whether objects following those paths hit each other is a matter of timing and relative velocities, but they are constantly moving to intercept the other's path. So just like how moving along a curve in the third dimension can be viewed as moving along a straight path in the second dimension, moving along this now curved fourth dimension means it still feels like we are moving in a straight line through the third dimension. And just like how two-dimensional beings moving in parallel lines eventually meet one another along the surface of a sphere, us moving in straight parallel lines in space means we still end up meeting each other or crossing one's path within space-time. Think about how crazy that is. If we suspend a ball above the Earth's surface, it's moving in the same direction as the Earth through space. Let's even freeze the rotation of Earth so we don't have to worry about the angular velocity affecting our ball's movement. Now when we look at the ball and the Earth, they are both clearly moving along two parallel paths through three-dimensional space. So there's no reason for them to cross each other's path. But when I let go, as they travel through space-time, just like how we saw with the friends walking on the sphere, because they're traveling along a curve in a higher dimension, the ball and the Earth end up running into each other despite traveling parallel with each other. And this is the fundamental concept of gravity. This becomes abundantly clear if we change our perspective. If we look at our two friends walking along in two dimensions, it looks like they walk into each other. However, if we remove any reference to their velocity, because they are walking the same speed, it simply looks like they are gravitating towards each other for no reason. The same thing applies to our ball and Earth. As they both whiz past, it's clear that, oh okay, they're moving along a curve on the fourth dimension and thus converge. We can see both of their horizontal and vertical movements, but to someone standing on the Earth, the ball appears motionless as if it's not moving through space at all. The only difference is that the ball's path through space-time converges with the Earth's path. And even though it appears as if the ball is motionless on the ground, since both the Earth and the ball are still moving through space-time, they're still constantly colliding. Finally, let's go back to our trampoline example, and I want to explain my original confusion with this model in case anyone else had or has it. As we roll a ball around our space-time, it's clear that we see the curve of orbits and we see that, oh yeah, things fall down the well, as it's called. But why does it need to? If gravity isn't a tangible force, why, if I place a motionless ball here on the trampoline, does it have to roll towards our planet? And this is where my mistake was. You see, before when we talked about lower dimensional beings moving about, there's nothing stopping them from stopping themselves or just deciding to sit down. But remember, everything is always moving through space-time. So the ball placed on the trampoline has to move because everything in space-time moves. And our planet in the middle of the trampoline isn't motionless either. It's also moving through space-time at the same speed as the ball. And once you see the trampoline like this, well, I hope it clicks and it makes sense why something would just fall as we perceive it straight down. So remember, if it feels like you're stuck in a rut or not making any progress, the universe is always there behind you, moving and pushing you forward.